the principles of warfare. So how to achieve a concentration of force? Clausewitz tells us in chapter 1, book 6, quote, defense is the stronger form of warfare, close quote. Another quote, it is easier to hold ground than to take it. This is because attackers have to move across exposed ground, while the defenders take advantage of cover and are able to shoot at the attackers. Here you can see British artillery operating in Borneo in 1964. The solution and the method is maneuvering. This is how you achieve concentration of force. You maneuver forces to attack at the opportune moment and at the decisive point where the attacker's force ratio is maximized against the defenders. And this is how you achieve the concentration of force and all the mathematical benefits that go with it. This leads us to the third principle of war, the initiative. This is also called mobility and maneuver. The third principle of war, initiative, is the ability to move first. And it matters because it permits one side to place its forces more favorably than the other side to achieve the desired concentration of force. This is one major reason why military leaders are often so eager to escalate disputes to war. Not because they enjoy the violence, but because to lose the initiative could be fatal. The first move gives tremendous advantage to the attacker. Here you can see a US F-111 dropping bombs. This chart depicts a NATO assessment of the first move advantage with regard to tanks firing first. Sort of a complicated chart. If you look on the left vertical side, you'll see a percentage, and that's the probability that the first shell fired from a tank will hit and destroy its target. And then horizontally at the bottom, you see ranges in meters and yards. And you've got three lines, a red, a black, and a blue. The blue line represents a stationary tank firing at a moving target using a heat round, a high explosive anti-tank round. This is the plasma round I was describing earlier. So if you look at 1,000 meters against a moving target, there's a 30% chance that the first round will hit. If you look at the black line, that's a stationary tank firing at a moving target with an armor-piercing, fin-stabilizing, discarding sabot round. That's the tungsten core round that I showed you on the weapons lecture. This is a round that achieves its damage by kinetic force. Here, at 1,000 meters, you're looking at an 80% chance because the ballistics of an APF SDS round are highly accurate. And finally, if you have a stationary tank firing an APF SDS round against another stationary target at 1,000 meters, you're looking at an 85+% chance of hitting in the first round. In other words, there's an enormous payoff to getting off the first round. Now, tanks can shoot out to 5 kilometers, but the average engagement range, because of buildings and undulating ground and trees, is about 1,000 to 1,500 meters in Central Europe, which is the likely battlefield between NATO and the Soviet Union during the Cold War in the 1980s. So this is just one tactical evidence of the advantage of a first mover advantage from a tactical standpoint. The same applies to missiles, tanks, aircraft, ships. It applies less for more dispersed ground forces hidden in the camouflage of ground terrain. Now, Boyd was an Air Force analyst, and he generated a cycle called the OODA cycle, which is the cycle that pilots go through when they're involved in a dogfight. And this cycle of analysis has been applied from air warfare to ground warfare and to sea warfare, with the thinking that the side that makes the faster decisions on the battlefield are better able to take the initiative and exploit an enemy's weakness. And this was a major focus of NATO, because NATO thought that during the Cold War, the Soviet Union's decision-making process was very slow. So NATO practiced conducting operations many cycles faster than the Soviet Union. The US, in fact, developed TOCs, or Tactical Operations Centers, that would do the planning for the commander and then give the commander a plan that could then be implemented before the enemy could react. So while the enemy was slowly maneuvering into position, the American forces would be counterattacking from unexpected angles. So this cycle consists first of being in the environment, observing one's position in the environment, orienting oneself with regard to the enemy in the environment, making a decision, and then acting back onto that environment. So you can understand how a pilot would do this if they're caught in a dogfight with an enemy aircraft, but this equally applies to ground forces maneuvering around each other. Now, maneuvers occur in geographic space, both for land, sea, and air warfare. But not all geography is equally accessible to all movement and visible. So, geographic factors that must be considered are as follows. We can make a designation of key terrain. This is terrain whose occupation will influence the outcome of the battle. This could be a hill or a position that gives you a vantage, like a tall building. Vital terrain is terrain whose occupation will decide the outcome of a battle. For example, if you have an enemy landing on a beach and you're able to capture the hill nearby, and that hill has a commanding view of the beaches, then it's vital terrain. Capturing that hill will win the battle for you. You don't need to capture the beach, you capture the hill, and from the hill you can bring fire onto the beach. There are obstacles, and these are blockages to maneuver. There are points of observation, which are locations that allow you to see what's happening on the battlefield. If you want to bring in accurate artillery fire, you want a forward observer at that location. There are fields of fire. These are geographic locations that permit open arcs of fire that allow you to bring fire onto the enemy. You could create killing zones. These are areas in which the enemy advances that are constrained geographic areas where you can maximize your fire. There's a consideration of cover and concealment. Cover gives you protection against incoming fire. Concealment doesn't give you protection, but it hides you so the enemy may not engage you. You can see a typical NATO symbology applied to a map in West Germany. So here we have an illustration from the Canadian Forces pamphlet on the advance to contact. This is a drill that 10 soldiers, a section of soldiers, will go through. So imagine you're commanding 10 soldiers and you come over a crest of a hill, and this is what you see. So what you want to do here is apply the principles that we looked at before. Your goal is to command this terrain. So first of all, we have key terrain that allows us to command this area, and it's the crest of the hill we're sitting on right now. On the other hand, if there's an enemy that's on the far hill in the distance, they could bring fire down into this valley. So that could also be considered key terrain. Perhaps also vital terrain, where if the mountain is controlled, the mountain that we're facing in the distance on the far horizon, it could command all of the terrain in the valley by bringing down artillery fire. Now, obstacles to maneuver, well, we've got a cliff on the right side. We've got some hills on the left side. We've got a fence running down the center. We've got some rocky terrain right immediately in front of us and in the corner to our right. Points of observation, well, there might be an artillery observer in the farm silo up in the center. Cover and concealment, well, we have some undulating ground, and this means we've got dead ground. Dead ground is ground that you can fall into and hide in the shadow of it. And so the enemy might know that you're in the area, but they can't bring accurate fire down on you because you're hiding on a reverse slope. That's on the slope on the other side of the enemy. A forward slope is when you're in front of the hill and the enemy can see you. There are different philosophies. I mean, if you're on the forward slope, everyone can see you, but you can see everyone. And this is what the U.S. Army likes to do. They bring in their long-range anti-tank rockets, they put them on the forward slope, and they shoot at everything they see. The U.S. Marine Corps typically operates much more lightly, and so they typically deploy on the reverse slope. They have shorter range weapons, and they wait for the enemy to come over the crest of the hill, and then the enemy is silhouetted against the sky, and they're encountering Marines that until that instant they weren't sure where they were, and then they're overcome by short-range, highly effective firepower. Now we can imagine there's concealment in the trees and bushes on the left and the right, and there's probably concealment also in the farmhouse in the center of the map. A consideration about terrain is the importance of doing reconnaissance. There's a famous saying, time in recce is seldom wasted. In battle procedure, which is the procedure that leaders go through when they're given orders to conduct an operation, they have to sit down and consider their orders. Then they do a reconnaissance, which is to go over and take a look at the terrain of the battlefield, and then they come back and they do their plan, and then they distribute their plan, their orders to their soldiers, and the soldiers do a rehearsal, and then the force deploys to a phase line and an assembly area, and then they cross over and they attack the target. Terrain is always more complex than what is depicted on a map, and it's so important to go and physically look at the terrain. If you were to go to a university or a high school football field and lie down on that pitch, you would see that even in what we imagine to be a very flat football field, there's curvatures. Sufficient curvatures that you could probably hide in some of the undulations of the terrain. Terrain is super complex, and it's never as simple as depicted on a map. And it's important to go and take a look at the terrain. The main considerations are, where is the enemy going to be in the terrain? How will they make use of it? And a second consideration is how to place weapons to maximize their arcs of fire, to allow them to benefit from cover and concealment. And how do you maneuver them on the battlefield? In fact, there's terrain everywhere. There's even terrain in space, what we call the Lagrange points, L4 and L5. The Lagrange points are the intersection gravitationally between the Earth and the Moon, which maximizes the possibility of a satellite deployment, which means there's an equilibrium point where the gravity of the Earth and the Moon balance each other out, and it allows a satellite to remain in that location with great stability for a very long time. And so it's a prime location for satellite deployment, and therefore a target of attack at times of war for countries that want to remove other countries' surveillance instruments. Here you can see an actual photograph from a probe of the Earth and the Moon, just to give you a sort of a scalar sense of how big they are. And you can see the Moon is actually quite far away. And you can imagine the Lagrange points as dynamic planes that exist between these two bodies. So there are 7 classic maneuvers, which are a very important aspect of warfare, particularly in land warfare. And organizations generally face a single direction where they have their weapons pointed one way to maximize their force, and they have a rear vulnerable area where they have their command and their logistics and their medical and their communications forces. This is done because militaries don't have enough resources to face in many directions and preserve their military force. And secondly, it's convenient to place vulnerable resources like supplies food and ammunition in the rear where they can be protected. Here you can see the Soviet Kiev cruiser carrier during the Cold War. The first maneuver is penetration of the center. Here, the goal is to seek to divide the enemy, but to threaten them at the same time with the danger of envelopment. This was the maneuver applied repeatedly by Napoleon Bonaparte, most classically at the Battle of Austerlitz against the Austrians and the Russians, which was his greatest victory. Ultimately, Napoleon's enemies were able to adapt to this by not separating their forces. Essentially, Napoleon would threaten to outflank the left and the right sides, and the enemy would then thin out the center, and then Napoleon would burst through the center at the decisive time, and the entire army would collapse. And at the Battle of Leipzig, the Prussians, Austrians, and Russians were able to defeat Napoleon without succumbing to this one maneuver of his. And Sir John Wellesley was able to defeat Napoleon at the Battle of Waterloo, also by being very careful not to stretch out their forces against Napoleon's flank attacks. The second maneuver is the envelopment of a single flank. Here you would roll up against a single flank and then roll up the enemy. Now this is difficult to do because you need to be able to get into the enemy's rear without their reserves or without their force attacking. This is the technique applied by General O'Connor, the British commander of the British forces in Egypt, against Italy in 1940 and 1941, which resulted in a catastrophic defeat of the Italians in Libya. O'Connor basically drove deep into the Libyan desert from Egypt and then turned against the coast behind the Italian forces, who then collapsed. The third maneuver is the envelopment of both flanks. Here you have to hold the enemy in the front, and then you drive around the left and the right flank, and then you're able to basically enclose and destroy the enemy. This was Hannibal, the great Carthaginian general's maneuver against the Romans at the Battle of Trebia in 218 BC. And you can see that battle depicted on the right. It was a catastrophic defeat of the Romans. The fourth maneuver is the attack in the oblique order. You saw this already in the attack by Epaminondas against the Spartans at the Battle of Leuctra in 371 BC. It was copied by innumerable classical and early modern European leaders. So it essentially consists of holding one part of the enemy with a weak force and then pushing in with a very strong force against the other flank. And it's typically done by maneuvering at an angle so that the weaker side never makes contact with the opponent. This is a strategic depiction of Alexander the Great's conquest of the Persian Empire. And this technique was applied repeatedly at the Battle of Granicus in 334 BC, which you could see near the crossing of the Dardanelles in Turkey, at Issus in 333 BC, which is near Antioch at the intersection of Turkey and Syria, and finally at the Battle of Gaugamela in 331 BC, which is near Erbil in Iraq. Here you can see the Battle of Gaugamela, or Arbela, on October 1st, 331 BC, where the much smaller force of Alexander the Great basically moved at an angle against Darius, who is located on his chariot in the center position of the Persian army. And most of Alexander's army was not in action against most of the Persian army. Rather, just a small portion was hit, and the rest of the Persian force was held at a distance. You can see the Persian immortals in the top right, an elite bodyguard that protected the Persian leaders for many centuries. The fifth maneuver is the feigned withdrawal. So here, one side pretends to withdraw, and it provokes the other side into a disorganized pursuit. And then you turn your forces around immediately, and you crash into and you envelop this disorganized attacker. A feigned withdrawal can only be done by forces that are very well trained and significantly drilled. The Mongols use this tactic against both the Russians and the Hungarians with dramatic effect. In the European armies would follow into pursuit. They would lose their formations, they would lose their defensive strength because they didn't want the Mongols to escape. And then the Mongols would then turn around in a great coordinated fashion and surround this disordered enemy and destroy it. The classic application of the feigned withdrawal, however, is again the Carthaginian general Hannibal at the Battle of Cannae against the Romans. And this is possibly the greatest Roman defeat in their history. The Carthaginians and their allies basically had their backs up against a river, and they basically feigned a collapse, and the Romans fell into that collapsed base, and then Hannibal was able to maneuver his flanks around the left and the right of the Roman force, surround it, and utterly destroy it. The Battle of Cannae. A sixth technique is the attack from a defensive position. In this situation, you have the enemy attack you, they're worn down, and once they're worn, then you do your counterattack. And this was essentially attacked by Moltke in the Franco-Prussian War. The Prussians had calculated that the defense was always stronger than the attack. So the Prussians would maneuver in a location that would compel the French to leave their position and attack. Typically the Prussians would try to maneuver behind the French. Then the Prussians would absorb the attacks from the French forces, and then they would counterattack when the French forces were spent. And this is how the Prussians defeated the French at the Battle of Sedan and ultimately took Napoleon III prisoner. The seventh maneuver is the indirect approach, and this was popularized by the British armored writer Little Hart and J.F.C. Fuller, who is another British writer on armored warfare, who had some influence on the Germans. And the principle was to use armor to go a very broad sweep around the enemy and attack them from a completely different location. Probably the best example of this attack is the German Field Marshal Erich von Manstein, who applied this technique, outnumbered overwhelmingly by Soviet forces around Kharkov. So he basically allowed the Soviets to attack, and then he maneuvered his armored forces in a very wide swing that allowed him to then get into the Soviet rear and cause the Soviet front to completely collapse, and then Manstein recaptured all of the territory that the much stronger Soviet force had captured. This then brings us to the associated fourth principle of war, which is called the economy of force. This means, very simply, you maximize the use of scarce resources. You're never going to have enough military force. You're never going to have enough soldiers or aircraft or artillery. And you have this constant problem of too much enemy. So the economy of force means that you never apply more force than is necessary. You always apply the minimum force necessary so that you can save forces and apply them somewhere else. So ultimately, it's going to be a game of balance. You want to achieve a concentration of force against the enemy by putting all your forces in one place, but you can't do that because you need some forces elsewhere to keep the enemy distracted. So the economy of force reminds us of the problem of scarcity. We want to have concentration of force, but we also want to have forces elsewhere, and those forces are going to be kept at a minimum level so that we can maximize our focus on the point of attack. So it's the problem of maneuver. Quote, an advancing force can move toward its objective on one of two roads, one good and one bad. The first broad, direct, and well paved, and the second narrow, circuitous, and unpaved. However, the good road is apt to be bad precisely because it is the better road, whose use by the advancing force is more likely to be anticipated and opposed. This is from Little Hart's book, Chapter 20, in his description of how to pursue the indirect approach. And he basically has two steps. One, choose the line or course of least expectation, and then exploit the line of least resistance. So it's about where the enemy thinks you're going to be. And it becomes a game of what I think you think, ultimately. And the better commander is going to be able to disentangle that and choose correctly. In war, however, the game is complicated by the fact that, of course, the enemy is trying to do the same to you. And there's actually a mathematical and philosophic solution to this, which we call the mixed game strategy. You can see here a picture of a cartoonish depiction of the Maginot Line, which is a fortifications the French built against Germany in the 1920s and 30s to stop a German invasion across the Upper Rhine. A second very important concept that needs to be understood if you're to understand warfare, particularly nuclear warfare, is the mixed game strategy, which is the logic of probabilistic warfare. This is important for two reasons. One, it has a core powerful effect in the same way that the Lanchester equation does. And number two, more importantly, it is completely counterintuitive and opposite to what a normal, commonsensical individual would choose to do. Now, in warfare, like in, say, boxing, it's a competition. And things are not always equal. If you were to face off against, say, a boxer, and let's say their left arm was much stronger than their right arm, right? And you wanted to defeat them. Well, obviously, you would compensate by trying to protect yourself more from their stronger left arm than their weaker right arm. And the logic of that is to make them indifferent between the two choices. And you want to make them indifferent between the two choices because then they can't exploit you. Now, that sounds like sort of a fairly simple proposition, but it's actually possible to mathematize it in such a fashion that we can get precise instructions on how frequently we're supposed to play what we do to counteract what they're doing. Now, the equivalent in warfare on land would be, say, you're going to be attacked on your broad front, and you're protected on one side by mountains, on the other side by a forest, and so you would privilege putting more soldiers in the forest than you would in the mountains, because your defense is basically the very strong defense of the mountains plus some soldiers versus the very strong defense of a lot of soldiers plus a few trees, and it would balance out, and so the enemy would have no advantage advancing on you. And so we want to be able to mathematically precisely apply that. Now, John Nash of movie fame was a game theorist, and he actually came up with a mathematical theorem which showed that the mixed game strategy is the most efficient way of specifying how to make your opponent indifferent between their different choices. Now, there's always a better solution. The best solution is to have a spy in the enemy camp and to know where and when they're going to launch their missiles. There was an espionage case in the 1980s, which is probably the most damaging espionage infiltration of the U.S. ever. There was a family called the Walker family. A whole family were involved as spies for the Soviet Union, and they gave the Soviet Union the codes for some of the launches for the U.S. nuclear missiles. It was the most damaging espionage case in U.S. history, besides the Rosenbergs, who funneled Manhattan Project nuclear weapons development secrets to the Soviet Union. So we don't have a spy necessarily, and if you don't have a spy, then John Nash's solution shows that this is the next best thing. So military outcomes are the result of strategic interaction because you've got two players that interact. And so we're going to look now at games theory to see what the different steps are we have to go to ultimately come to our mixed game strategy solution. So you might recall the prisoner's dilemma. The story is, of course, the narrative that two individuals go to rob a bank. They're arrested in the lobby before they even begin to rob a bank, but they're charged with robbing the bank. The police then isolate them, and the police incentive, of course, is to have them go to jail. And if they only get one of them to go to jail, they need to make an example, so they put them in jail for an extra long time. If they don't manage to get them to admit or to finger each other, then they can at least charge them with trespassing for 3 months. If both of them are discovered to be thieves, then they would both get 5 years. Now, the prisoners can't communicate, they can't coordinate, they have to sort of anticipate what the other would do. And so the question we have for a prisoner's dilemma game like this is, what is the outcome going to be? Okay, so here we have two players, player A and player B. We've got two columns of choices called strategies for player B, cooperation and defection. For player A, we have two rows of strategies or choices called cooperation and defection. The diagonal lines that are there to remind you that the lower left payoff or utility is for player A, and the upper left utility or payoff is for player B. Now here, we're talking about prison time, so the lower the number, the better. So 0 is better than 3 months, 3 months is better than 5 years, and 5 years is better than 6 years. So how do we play the game? So player A has a choice between cooperation or defection, the red row and the green row. And the way that we solve it is called seeking dominated or dominant strategies. Okay, we want to find out if one strategy is superior to the other. So let's compare. The way we do it is we compare the values in the different cells. So for player A, we look at the column for player B, the first column, and that would be on the left. And we compare 3 months in cooperation with 0 time in jail in defection, the green versus the red. And clearly player A would prefer to have no time in jail at all. Then we go to the next column of player B, and we compare the two values for player A's choices, 6 years, which is in green, for cooperating, or 5 years for defection. And obviously 5 years is better than 6 years. So player A will always choose red. There's no reason to choose green. Now player B again has the same two choices, red versus green. It's a symmetrical values, and we can again do the same comparison. 0 time in jail is better than 3 months in jail, and 5 years in jail is better than 6 years in jail. And so player B will always choose defection. So by eliminating dominated strategies, we can then know what strategy they would never play. So this then leads us to the Nash Equilibrium. Now the definition of a Nash Equilibrium is, once you've eliminated the dominated strategies and you have a dominant strategy, then the dominant strategy reveals to you, when they intersect, what the Nash Equilibrium is. And a further check on the Nash Equilibrium is, once you have that Nash Equilibrium, neither player will have any incentive to change. All right, they're not going to change their strategy. If you were to say, hey, do you want to change now again? Do you want to change a different strategy now that you've seen the outcome? If they say no, then that is definitely the Nash Equilibrium. If they say yes and they want to stay, that's the Nash Equilibrium. But if they want to change, then we have a problem called cycling, which is described by the Condorcet paradox, which is not the subject of this course. So here we have player A choosing defection. Here we have player B choosing defection. So here we have the intersection of the strategies chosen by player A or player B, the two dominant strategies. They overlap, in which both players go to jail for 5 years. This is the Nash Equilibrium. And we can confirm it's the Nash Equilibrium because we can offer player A or player B a choice of a different choice. So player A, would you like to go from defection to cooperation? Well, let's see the playoff change. If player A goes from defection to cooperation, which is the row of defection to the row of cooperation, they'd go from 5 years to 6 years. And player B, same thing. If you could offer them a change of their strategy from the column of defection to the cooperation column, they would go from 5 years to 6 years. So there's no incentive for them to change. Therefore, this is confirmed as a Nash Equilibrium. Now, it's a suboptimal outcome. It would have been far more intelligent for player A and player B to cooperate and each get 3 months. But the lack of ability to coordinate led them to this result. Two players fighting each other are not cooperating, but they do have an incentive to exploit each other. And you can design a game that shows that attempt to exploit, which is what happens in warfare. Now this is a depiction in a military journal of an operations research application of an early form of mixed game strategy. During World War II, some of the preliminary insights of mixed game strategy solutions emerged out of studies done by von Neumann and Morgenstern, and it influenced things like submarine patrol patterns. Here we have an application of the problem to the Japanese advance from Rabaul in February 1943 to Leh on New Guinea. And the Japanese have essentially a choice of going from the northern route or the southern route in a convoy. And these two choices intersect with the U.S. Navy, which was directed by General Douglas MacArthur. He ordered General Kenny to interdict the Japanese resupply efforts. And the intersection was for the Americans to attack the northern route or the southern route. And if they got it wrong, then the Air Force would be in the wrong location, and then there would be a delay. Now, historically, ultimately, the Japanese chose the northern route. You can see here the intersection of the Japanese and the American choices. The Americans can choose to go north or south, and the Japanese can deploy north or south. And because of the geography, it's not a symmetrical outcome. And the payoff for the Americans is the number of days of bombing they would have against the convoy, whether it would be 1 day, 2 day, or 3 days of bombing. And we can use this simple interaction to then make a determination on what the Americans should do to maximize their maneuver. Here you can see a strategic form representation of the intersection of the northern and southern routes for the strategies by the Japanese and by General Kenny. Here's a second situation, which is the breakout by the Americans from Avranches, from Normandy after the D-Day landings. So this is the situation on August 7th, 1944. You've got the Americans breaking out against the Germans. The American goal is to seek an action that'll intervene against the German reserves. The American General Bradley was tasked with the destruction of the enemy, which was the 9th Army under General von Kluge. So here you've got a much more complicated list of preferences, and this is the preference of the American forces. They want to hold the gap that they've broken up that allows them to pass out of Normandy, although it risks possible German encirclement. There's a strong pressure on the German withdrawal. There's moderate pressure on German withdrawal, weak pressure on German withdrawal. They want to hold the gap, and ultimately the gap would be cut. So 6 is the worst possible outcome, and the 1st is the best possible outcome. And the Germans have the opposite preference ordering from the Americans. Now the choices are for the Germans to withdraw and to maintain the strength of the line, or to attack the gap, hoping to close it and keep the Americans within Normandy. The Americans have 3 choices, which is to move their reserves to reinforce the gap, or to ignore the gap and to order their reserves eastwards towards Paris, or the 3rd choice is to hold the reserve in place 1 day to reinforce the gap if necessary, or to strike eastward. In other words, to wait to see what they should do. And again, you can see the intersection between the 2 German choices and the 3 American choices, and it translates into the gap holding or being cut. So obviously the Americans don't want the gap to be cut by the Germans, but in order to do what they want to do, which is move east and attack the German reserves, they're going to have to risk it. Otherwise, they can sit at the gap and protect it, but it's a low-risk strategy, but also a low payoff benefit to the American command. So here you can see the strategic form game representation, which can be done, for any battle in which you've got 2 sides. You've got the 2 German choices and the 3 American choices. And this is a more formal strategic form representation of the battle. If you were to play through, you would see that Bradley would eliminate and reinforce as an option, because this is the dominated strategy. And there's no solution by comparing alternatives. In this particular case, you'd end up with a mixed game strategy solution. So let's take a look at a mixed game strategy in an actual historical event. This is the Battle of Dezful, 1980, at the beginning of the Iran-Iraq War. We have Iraqi armored forces advancing into Khuzestan or Arabistan in Iran, and the Iranian forces facing off against them. Here you can see an overhead view just on the foothills of the mountains on the Iranian frontier, on the northern part of the Arvandrud, or the Shuttle Arab waterway between the Iraqis and the Iranians. So I've simplified the choices. Both sides have a choice of moving forward, left or right, or withdrawing. Now, because the forces are not of equal strength, the Iranians are weaker in this particular battle, but they benefit from the terrain because they're advancing in home territory. You have asymmetrical payoffs. The Iranians are more infantry, the Iraqis are more armored, and so they also get different advantages from the terrain. And so it is the intersection of these four choices that are then going to be represented in the numerical values on the next slide. So here we have a hypothetical game, and I've made it a bit more complicated because we want on this table to do two applications. We want first to apply the technique of dominant strategies to eliminate strategies that would never be selected, and then we want to further apply a mixed game strategy. So let us proceed. So let's make this player A and let's make this player B. It's actually arbitrary at this point. Doesn't really matter. We have rows and columns. So let's compare the values. Between forward and right, which strategy would be preferred? Well, we see that 2 and 2 are the same. They're equivalent. 1 and 1 are the same. 3 and 3 are the same. But you know what? 2 is better than 0. So player B is never going to choose this row. And by eliminating the row as his choice, the numbers there also are irrelevant for player A. Player A is never going to encounter those outcomes because this choice will never be made by player B. Now, doing this search for dominant strategies does involve a certain trial and error. Right? So you have to go back and forth to solve it. Although this particular table is much simplified. So let's compare left and withdraw. Well, 2 is better than 0. 2 is better than 0. 0 and 0 are the same. And 3 is better than 0. So, you know what? B is never going to choose withdraw either. Just not possible. The payoffs there are not very good. Here, of course, it's the opposite of the prisoner's dilemma. The player utility is for the highest possible value. So let's take a look at player A now. Player A has a choice between 2 versus 1, so 2 is better than 1, and 1 versus 1, which is the same. So player A is never going to choose to go forward. Let's compare now 1 versus 0. Well, 1 is better than 0, and 3 is better than 0. So player A is never going to choose to withdraw. The net effect of this is to leave us with just the 2 central cells, or these rather the 2 rows and the 2 columns. That leaves us the 4 central cells. So let's see if we can't come up with something here. Do we have a dominant strategy? Let's start with A. Well, 2 is better than 1, but 3 is better than 1. Oh, that's a problem. This is called cycling. It means that there is no dominant strategy. All right, so let's take a look at B. Maybe there's a solution here. Maybe we can unlock with B. So for B, 2 is better than 1, but 2 is also better than 0. So we have cycling among both actors, which means we cannot use a dominated strategy to solve. So what we're left here with are the core choices from that strategic game. Now you'll notice the feature with this central square is that we have no dominant or dominated strategies. So for example, if we were to look at player B and we were to compare their choices, we notice that 2 is greater than 1, but 3 is greater than 1. So the 2 strategies, they don't dominate each other. As well, for player A, we see that 1 is less than 2, but that 2 is greater than 0. So their 2 strategies of left and right also don't dominate each other. So we're at sort of a logical impasse. But we have a mathematical solution. It's called the mixed game strategy solution, and it involves a little bit of algebra. The way we should conceive of this is like a boxing match. You have 2 people fighting each other, but their arms are not symmetrically equal. They're not equally strong. If someone were to attack you and they had a stronger right fist and a weaker left fist, right? You would end up in a game of, I want to think what they're thinking about what I'm thinking about what they're thinking. Because if you always defend against the strong right punch, their left punch is going to hit you. And even though it's weaker, it's going to get through more often because you're not defending against it. So mathematically and conceptually, what you want to do is you want to divide your defense so it's proportional to their stronger right arm and their likely more frequent weaker left arm, right? And so psychologically what you're doing is you're making the opponent indifferent between their choices. It doesn't matter that their right arm is stronger because you're going to maneuver in a way that causes them to swing with the right arm less. Because you're going to defend disproportionately against the right, but not so much so that it gives the left an advantage. So that's the type of solution we're going to create using algebra. Now another way of thinking about it is militarily. Here we have a depiction of a battlefront. And you can see on the left side there's a little forest. In the center is an easy road leading on to the horizon. And on the right we have these difficult mountains. Now defensively, if you're trying to protect against an advance, the mountains are the easiest. You wouldn't need a lot of soldiers in the mountains. The road, you need to barricade it. You need to put a lot of soldiers there because it's such an easy route. And the forest, it's not as easy as the road, but it's a lot easier than the mountains. So you could put all your soldiers on the road, but then it would leave the mountains exposed, and then the enemy would sneak through the mountains and attack you from the rear. So the idea is not just to defend one of these. The idea is to defend all three, but in proportion to how easy they are to exploit. So you'd put the most soldiers on the road. You'd put a medium amount of soldiers in the forest, and you put a very small number of soldiers in the mountains. So that the geography plus the soldiers in the defense will make the opponent indifferent. It doesn't matter whether they go through the forest, the road, or the mountain. It'll be equally difficult. Because the difficult terrain will be counterbalanced by a small number of soldiers, and easy terrain will have a lot of soldiers defending it. So that's what we're going to do here. Now, a note on the terminology. Traditionally in mixed game strategy, the variables that are used are theta 2-1 and theta 2-2 for actor B, and theta 1-1 and theta 1-2 for actor A. I like to do it this way because I think it gets you into the mindset of the terminology used by the creators. And one of the creators of this, of course, is John Nash. But you could easily replace these with X and Y and A and B, and it'll be a lot easier. Theta 2-1 or theta 2-2 are not numbers. They're just a name. The numbers here are just a name. So it's a variable identifier. That's all it is. So we have here these values. We know that we have no dominant or dominated strategies, so there's no canceling out of strategies, so we have to solve this. Now this is one of the surprising theorems that comes out of mixed game strategy. These values are diametrically opposed to each other in the sense that there's a zero-sum game. Any victory for B is a loss for A, and we have to have that assumption for this to work. So these are two adversaries that have no incentive to cooperate. They're at war with each other, or they're in conflictual relations. So the logic in analyzing this requires you to make the opponent indifferent. Okay? That's not the best outcome. You know what the best outcome would be? If you had a machine that could read the mind of your opponent. If you had a spy in the enemy camp who could secretly tell you what they're planning to do, that would be the best possible outcome. But we don't have that. And so the next best thing is to structure our behavior and make the opponent indifferent. And there's a theorem that proves deductively that that is the best solution. Right? Now this is the peculiar thing. It doesn't matter what your values are. It matters only what the opponent's values are. So we're going to use the opponent's values against them. We're going to take the distribution of gains for the opponent and use it to structure our behavior. We're not going to use our own values. It's completely counterintuitive. Right? But even though the values are not symmetrical, because there's a zero-sum game, we can do this. So, let's go construct our equations. Okay, so first we're going to do it for player B. Now recall, the top right are the values for player B. So we're not going to use those values. We're going to construct player B's values looking at player A's numbers. Okay? And we do that here. So we're going to take theta 21 and theta 22. These are the two variables for B. All right? And these represent how often B is going to play the left strategy versus the right strategy. All right? These are the things we want to know. All right? We want to know how often to play this versus that strategy. And this equation is going to tell us to do that. So we're going to take theta 21 and multiply it against A's value, plus theta 22, and we're going to multiply that against, again, player A's value. So we're going to get here theta 21 times 1 plus 2 times theta 22. So theta 22 times 2. Okay? That is the left and right strategy. The next step is to apply theta 21 and theta 22 to the other two sets of values of player A. So it's going to be 2 theta 21, because here we're going to have theta 21 times 2, plus theta 22 times 0. I'm actually going to get rid of these because I think these are confusing and not helpful. So these are the two formulas. Now to solve the equation, we make them equal to each other. So we're going to take this here and put this formula here into this part of the equation, and this formula here into this equation, and we're going to end up with theta 21 plus 2 theta 22 is equal to 2 theta 21 plus 0 theta 22. Now remember, we can replace these with x and y. It'll make it a lot easier to understand, but I want you to see it as it was intended in the beginning. Now, do you remember the pizza rule? Right? Do not forget the pizza rule. The pizza rule is the whole pizza is your part of the pizza plus my part of the pizza. Okay? And so we can break that down into your part of the pizza is equal to the whole pizza minus my part of the pizza. And we need this because we cannot solve an equation with two variables. We have two variables, theta 21 and theta 22. We need to get rid of one of them. And we're going to do that by substitution, and the pizza rule helps us do that. Okay? And remember, it's theta 22 plus theta 21 is equal to one whole pizza. But we can move the variables around to create this construct where we put all the values on one side so we can isolate theta 22. So let's go do that. Let's replace every instance of theta 22 with 1 minus theta 21. So let's go back to this equation here. We have theta 21 plus, we're going to substitute theta 22 with 1 minus theta 21 equals 2 times theta 21, and of course 0 times theta 22 is equal to 0. So we don't even have to substitute that. Now we have to multiply 2 into the bracket, so that's 2 times 1 is 2, 2 times minus theta 21 is 2 times is minus 2 theta 21. So it's going to be theta 21 plus 2 minus 2 theta 21 is equal to 2 theta 21. Now, the shortcut, of course, is moving terms on different sides of the equation, but what you're really doing is adding or subtracting on a given side, and you're doing it to both sides at the same time, and that's going to cause some of the terms to cancel out. And what you're going to end up with is 2 is equal to 3 theta 21, and then we divide both sides by 3, and we're going to end up with 2 over 3 is equal to theta 21. What does that mean? It means, first of all, that when we apply the pizza rule, we can see that theta 22 is equal to 1 minus theta 21. We know that theta 21 is 2/3. 1 minus 2/3 is 1/3. So we know that theta 21 is going to be 2/3, and theta 22 is going to be 1/3. Still, what does that tell us? It tells us that for player B, to make player A indifferent between their choices, player B has to randomly play theta 21 2/3 of the time, and randomly play theta 22 1/3 of the time. If player B deviates at all from that randomized pattern, they can be exploited by player A and do worse. There's a theorem that shows this is the most efficient way to achieve a positive outcome for player B, so long as player B does not have a spy in the camp of player A telling player B what player A is going to do. And there is a mathematical proof that deductively shows this to be true. So this is how you win the game. And if you don't roll the dice, if you play a hunch, if you play your favorite number, if you look at the stars and are inspired to deviate from randomness, and player A finds out, they will exploit you and you will do worse. This means that when you're gambling with people's lives, when you're launching nuclear weapons, when you're planning wars, when you're sending your submarine out to sea, when you're figuring out the search pattern for your ships, when you're attacking targets with artillery, you have to truly, sincerely, genuinely randomize. And if you don't, you're going to lose. But you can imagine, policy-wise, you could never publicly admit that this is what you're doing. That would be crazy, right? Soldiers randomizing their behavior. But this is the fundamental underlying nature of reality. And it's very often not intuitive and it's not realized. But we make these types of decisions every day, and the ones that do the best are the ones that play according to these rules. So let's now apply the same math to the other side. Okay? Let's solve for player A. Okay? Should not be too difficult. Again, player A is not going to look at their own values. They're going to use the values of player B. And as counterintuitive as that is, there's a proof for it. You can't fight physics, and you can't fight nature, and you can't fight the fundamental vocabulary of nature. All right, so for player A's got two variables, theta 1, 1 and theta 1, 2, and player A is going to be applying these two variables to the two values of player B. So we're going to have theta 1, 1 times 2, so that's 2 theta 1, 1 plus theta 1, 2 times 1 plus theta 1, 2 times 1, so that's going to stay the same. And then we're going to reapply to the other sets of values of player B. So it's going to be theta 1, 1 times 1, theta 1, 1 times 1, plus theta 1, 2 times 3, 3 theta 1, 2. And so we take these and we build an equation out of the two formula. So we have 2 theta 1, 1 plus theta 1, 2 equals theta 1, 1 plus 3 theta 1, 2, and there's our equation. All we have to do is solve it, and again, we're going to use the pizza rule because we've got two variables here, and we can't solve an equation with two variables. One of them needs to be substituted out. Okay, so here is how we're going to do it. We're going to substitute out theta 1, 2. Okay, so I'm going to reverse the, I'm going to put this here like this. I'm going to reverse the two equations here. So we're going to have 2 theta 1, 1 plus 1 minus theta 1, 1, because we're using the pizza rule. Here we're not using theta 2, 2. We're going to use theta 1, 2 is equal to theta 1, 1. So we're going to modify the pizza rule here for the other player. And this is equal to theta 1, 1 plus 3, open bracket, 1 minus theta 1, 1. And we carry that down to the next level. It's going to be theta 1, 1. We multiply into the bracket, so it's going to be plus 3 minus 3 theta 1, 1 is equal to 2 theta 1, 1 minus theta 1, 1 is equal to theta 1, 1 plus 1. Right? We're going to multiply 1 into the brackets. And this is going to work its way out to theta 1, 1 plus 1 is equal to 3 minus 2 theta 1, 1. This is going to end up being 2 is equal to 3 theta 1, 1. And it's going to end up being 2 over 3 is equal to theta 1, 1. So what does that mean? Well, it means that theta 1, 1 is going to be evaluated as 2 over 3. And so by the pizza rule, theta 1, 2 is equal to 1 minus 2/3. So theta 1, 2 is going to be 1/3. Now, these values are, they look symmetrical. Player A's got a 2/3, 1/3 split, and player B also has a 2/3, 1/3 split, but that's not always true. In some of the formulations of this, I have a 1/4 and 3/4. So there's no automatic dependence between the two players in terms of the proportion of these different strategies that they have to play. So you can see here, player B has their optimal strategy, and player A has their optimal strategy, and only by playing these optimal strategies will they maximize their outcome. Any deviation from this will result in possible exploitation by the other party member. So this might be very, very counterintuitive, but it's essential that whenever two sides are fighting each other under circumstances of uncertainty, that you're going to have choices that are difficult to make because they depend on the choice of the opponent and you're not sure what the opponent's going to do. This approach provides the optimal solution to winning under those circumstances. So that's the solution for the mixed game strategy. So the implication of the mixed game strategy is that Nash proved that it's the most efficient way of an individual player getting the maximum utility they can from their choices. The mixed game strategy is also the Nash Equilibrium. It tells us what the outcome is going to be in a game. Now you can expand this game to have more strategies. You can actually have more cells in a mixed game, not simply with two variables, although it becomes unwieldy with the pizza rule. You can have more players. You can extend that from a two-player to a three-player game by creating a three-dimensional cube. You can have a fourth-dimensional element to the cube, although it can't be represented and visualized. Now, of course, there's a difficult public policy implication, which is when you use nuclear weapons and you have any form of cycling because you don't have a dominant strategy, which is very certain when you've got two sides challenging each other, then you need to roll dice and embrace a random method to choose your strategy. We come from a culture which celebrates the application of the intellect. So we have this image in our head of Napoleon who sits down at Wagram on a chair around a fire and thinks about how to fight the battle. And then the next day, Napoleon's brilliance emerges and he completely defeats his opponents. That doesn't exist. It's a myth. If you are a wise commander, you will embrace the mixed game strategy and understand that when you're dealing with an opponent, to win, you have to gamble on people's lives with dice. So let's take a look at a summary of the principles of war, where we're going to cover the first 4 principles of war, and then we're going to take a look at the remaining 3. So the first principle of war is the selection and maintenance of the aim. Here you choose a single constant aim. Constant meaning it doesn't change over time. Key sub-values here are unity of command. You want to ensure all forces are operating under a single commander. It is almost never a good idea to have 2 commanders sharing power. There are rare instances, like in the case of the British Duke of Marlborough, the John Churchill, and his very sympathetic friend and occasional military subordinate, but more often partner, Prince Eugene, who served in the Austrian army. These 2 generals were remarkable in their friendship that allowed them to share military forces because of an incredibly high level of trust. And it's very, very unusual. Typically, however, when you've got 2 commanders, they're going to basically act against each other's interests, and you need a commander to essentially handle them. During the Second World War, American General Eisenhower had a lot of trouble dealing with the British Field Marshal Bernard Montgomery and the American General Patton. And these 2 guys were constantly fighting over scarce logistical resources for their own part of the battlefield. A second element is simplicity. Ensure the plan is simple enough that it can compensate for friction. Very complicated plans fall apart very, very quickly. Here in the picture you can see Sassanid warriors from Persia. The second principle of war is concentration of force. Here you want to ensure the matching of friendly strength opposite enemy weakness. It's also called mass. And the key here is do not subdivide your forces without reason. Some commanders who are particularly brilliant are allowed to violate this principle because they are brilliant. Napoleon would frequently break his forces into smaller contingents, and because of his incredible military intuition, these forces would reconverge at the right time, at the right place on the battlefield, and achieve victory after victory. Most commanders don't have this intuition and should never subdivide their forces. The principle is if the forces are subdivided, they should be close enough to each other in terms of time or range of weapons to provide mutual support. And so mutual support implies that these forces, if they're not physically in the same place, they can still be synchronized and mutually strengthening. At the top you can see Parthian horse archers. These are the nomads who conquered Persia. The third principle of war is initiative. You want to ensure forces are able to obtain a concentration of force before the enemy does. And there's a lot of elements here. The first is offense. Attack to obtain the initiative. This is necessary for victory. The Germans in the Second World War had a principle which was they didn't punish a leader for conducting an attack because many attacks fail. They would punish a leader for not attempting to attack. By constantly attacking, you keep your opponent essentially afraid, essentially insecure, and on the defense. So constantly being aggressive makes your opponent more vulnerable because they make mistakes trying to protect themselves. Attack, attack, attack. But don't be foolhardy. It has to be balanced and measured. Maneuver. Seek geographic advantage over the opponent. And this means reconnaissance. This means familiarity with the terrain. Mobility. Exploit the benefits that geography gives you to maneuver through it. So be flexible with regard to the environment and with regard to your forces. Keep your forces moving. Flexibility, which means be ready to adjust to the enemy at any time. Readiness. Safeguard against surprise. Expect the unexpected. In the First World War, France beat Germany at the Battle of Verdun and ultimately defeated Germany in the entire war. In the Second World War, German forces snuck into the Ardennes, burst through at an unexpected location, and defeated France in only 6 weeks. Guard against surprise. Exploitation. Exploit the enemy's weakness. Find out what it is and then maneuver against it. It may be a moral weakness, not a material weakness. Reserves. Always ensure reserve forces are available. Once your forces are in contact with the enemy, it's very difficult to disengage. And so if an enemy force appears by surprise somewhere, you'll have no forces to stop them and they'll drive into your rear. A principle the Germans had in the Second World War was always to create a reserve that was a third to a quarter of your force. So even if you're in a battle, pull back some of the element to create a reserve, because you could use a reserve to reinforce an attack, and you can use a reserve to block an enemy attack. So a good principle is always have some reserves available. But one warning, never reinforce failure, always reinforce success. And so if there's a part of the battlefield where you are losing, don't deploy your reserve there. Deploy it where you can do a breakthrough against the enemy. Surprise. You always want to deploy more rapidly than the opponent's ability to adjust. Now, surprise doesn't mean you never thought of it. Surprise can mean you just got there first. Here you can see Saxon footmen attacking a Norman horseman during William the Bastard's invasion of England in 1066. The fourth principle is economy of force. Balance the deployment of your forces between those that protect your force and those that are achieving concentration of force. An element is security. Ensure friendly forces and your planning are protected. This means have lots of patrolling to screen your forces so the enemy doesn't know where your forces are. Always think of security, of information. You don't want the enemy to know where you are. Deception. Deceive the enemy by means of a stratagem. This could be maneuvering. This could be attacking a target that you are trying to trick the enemy into thinking is your objective. Engage in diversions. Distract the enemy's efforts. Here in the picture you can see a Norman ship traveling to England in 1066. The fifth principle of war is reconnaissance. Ensure full information. Always maintain contact with the enemy. Do not lose track of the enemy's location. In this picture, you can see the Ottoman cavalry advancing in the 15th century against a Romanian monastery. The sixth principle is leadership. Ensure soldiers are aware of the goals of the war. In the First World War, the Canadians were the first army to distribute maps to every soldier in the military. The logic was if a soldier were to become lost, they wouldn't need to depend on their officer. They could continue and carry out their mission. An important aspect of leadership is focusing on the morale of the soldiers, ensuring that soldiers are psychologically taken care of. This requires providing care, basic necessity, but also explaining what the soldiers are going to do. Abusing soldiers in order to show strength is never a good leadership idea. It is almost painfully tragic looking at how poorly the Argentinian soldiers were served by their Argentinian officers in the Falklands War. The widespread abuse was one of the main reasons why the Argentinians fought much more poorly than the British soldiers, who were much better trained and led. Training. Ensure soldiers are trained appropriately for their task. Probably one of the best trainers of soldiers is German General Erwin Rommel, who wrote a book on the infantry. He wasn't an intellectual, but he was very good as a pedagogue. He knew how to train soldiers for different tasks, and that was his main strength. Here in the picture we can see the court of Genghis Khan. The seventh principle of war is logistics. Ensure the physical well-being of soldiers, of weapons, and of transport. Logistics is a very technical field, and we tend to think of generals like Alexander the Great and Napoleon as being masterful at maneuver. But primarily they maneuvered to defeat the enemy while also getting supplies for their armies. It's the reason Napoleon split up his force, so he could better cover the countryside and forage for his soldiers, permitting them to move quickly without having a large over-concentration of force in one place. Napoleon's campaign against the Gauls, which you can download an English translation of, because he wrote basically a weekly report back to his public in Rome, you'll see that he maneuvers mostly with attention to logistics. Logistics is super important, especially with modern armies. You cannot fight without bullets, fuel, and food. In fact, in the Canadian Army, stealing food receives the same punishment as stealing ammunition because it's a vital supply. So let's take a look at the military estimate. The military estimate is the way that the military is trained to go through a thought process when they're trying to come up with a plan to do something. And you will apply this when you do your TOOT, your tactical exercise without troops, which you will notice is on the last few days of the course. So when you write up the military estimate, the first step is the selection of the aim. What is the goal of the operation? The second step is listing the factors. What factors will play in the battlefield? Terrain, weather, the strength of the enemy, the defensive position, the amount of ammunition available, the information available, the opportunity for reconnaissance. All of these have to be listed down with their impact on the battle. Number 3, the summary of the deductions. You want to compact down the most important factors in order of importance, and then you want to turn these into 3 possible courses of action. In your course paper, you have a conventional wisdom, which is making predictions that are different from the alternative explanation. In a military estimate, we go for 3 different plans, almost contradictory plans. Remember, when you're coming up with your 3 plans, the enemy, in their summary of deductions, in their military estimate, is trying to predict what your 3 courses of action are. And then they're designing their courses of action based on your courses of action. So one of your factors and your deductions is what the enemy is going to do. And then in the 7th step, you justify the selection of the best course. Up on top, you can see the indigenous militia in South Africa during the Boer War. The British armed some of the locals to counteract the freedom of mobility that the Dutch Boer farmers were taking advantage of. So in the selection of the aim, you want to select only a single aim, never 2 aims, which can force unexpected trade-offs, and you want to maintain it throughout the entire estimate. The first and most important consideration is to get the aim right. If you don't get the aim right, you won't get the plan right. Here you want to put the limitations of the aim in terms of time and obeying the law. A limitation is not a second aim. It's basically foreclosing certain options to achieve that aim. Down below you can see a British military camp during the Boer War. In step 2, you want to list the factors. The enemy, the friendly forces, geographic factors, resources available, time and space, assessment of tasks. If you have to attack an island, you first have to do an amphibious crossing of the body of water that stands in the way. The priority of work, climate, and meteorology. Here the key question for the deductions is, so what? How does this affect the aim? Then you want to have your summary of deductions. This here is an artillery unit of British soldiers fighting the Boers. And then you've got your first course of action. You have a list of advantages and disadvantages for the plan. And then in the 7th step, you justify the process of selecting the plan. This here is a burned out, what I think is a set of buildings in a Boer settlement. And ultimately, you write up the plan. You describe in sequence the operations, and this would include that the operations is a success, or rather it'll include the indicators for what tells you that you've won and achieved your goal.